So when you talk about experimentation, you have to talk about accuracy and precision. And so we talk about accuracy being how close the measurement is to an actual value. So if your experiment involves finding the acceleration due to gravity, we know that the acceleration due to gravity is negative 9.8 meters per second squared. If you measure negative 9.75 meters per second squared, you might be considered more accurate than somebody who measured 8 meters per second squared. Now, the precision of a measurement is how closely you repeat those measurements, how often you hit the same target. It has nothing to do with what the real value is. They're just all clustered together and repeatable. Precision of a measuring tool is different than the actual precision of measurement. Precision of a measuring tool is going to depend on the actual tool itself, and it's generally half of the smallest division of that tool. So if you're using a ruler that is marked off in millimeters, then the precision of that ruler is plus or minus half a millimeter. And then uncertainty is how far the measurements vary from a standard or expected measurement. And so that could be because of the ruler you're using or some other built-in error in the system. So if we double back and think about just accuracy versus precision, here's a visual for you. The first bullseye, if you look at each one of those little dots, they're all fairly close to the center. They're all touching the little red center dot, so you might call that fairly accurate. The one on the right has a very tightly clustered area of dots, but it's farther away from the actual center of the bullseye. So the left one is accurate, even though they're spaced apart, and the right one is precise, but not necessarily accurate. Just remember, accuracy requires an actual target value. Another piece of experimentation is significant figures. Your answer can't be better than the values that you're calculating with. So you have to be careful about creating precision by writing down your entire calculator display. So here we have an example of finding the area of a circle, and it's carried out to 2 decimal places. So your answer can only be out to 2 decimal places, even though the calculator displayed a whole bunch more. So just remember that, remember to round correctly, and you'll be fine. Now, the uncertainty of measuring comes into the idea that you're going to carry these errors into calculations. And here we have find the circumference of a circle that has a radius that measures half a meter plus or minus 0.05 meters. So this is what we've decided our measurement is. And it's only good to about 5 centimeters. It's not a very good measuring tool. So the first thing we do is we calculate what the circumference would be with the value we think it should be, and you end up with 3.1 meters. And then to find the uncertainty, you have to find what that range is around 3.1 meters. So you go back in and do the calculation with the smallest possible radius and find the difference between the smallest radius circumference and the measured circumference. You do the same thing with the largest radius. And in this case, the largest radius comes up with the biggest difference of 0.4 meters. And so we want to use the biggest possible distance for our uncertainty so that we're being truthful with this. We don't want to cheat ourselves. And so the uncertainty in our circumference is 0.4 meters. So our circumference with uncertainty is 3.1 meters plus or minus 0.4 meters. So think about those things as we go into lab. They'll be very useful for you. All right, bye-bye.